Okay, so what is the relationship between the eigenvalues, the trace, and the determinant of a matrix A? Well, let's investigate this for ourselves using a simple 2 by 2 matrix A. So what we're going to do is, number one, find the eigenvalues lambda 1 and lambda 2. Then we find the trace TR. And finally, we find the determinant. Then we investigate the relationship between these three guys. Well, first of all, eigenvalues. Now, everybody knows that if a vector x is an eigenvector of a matrix A, then we can write A multiplied by the vector x is equal to lambda multiplied by the same vector x. We can also write this as A multiplied by the vector x is equal to lambda multiplied by I multiplied by the vector x. This doesn't change anything because x multiplied by the identity matrix I is just the same vector x. So we can also write this by transferring this to the other side as ax minus lambda I x is equal to what? Is equal to 0, because everybody is on the other side. We can factorize this to a minus lambda I multiplied by our vector x is equal to 0. Now, for this matrix here, for this equation to have non-zero solutions, this matrix here must have a determinant 0. Let me repeat that. In order for us to avoid non-zero, to avoid the zero trivial solution for x, the matrix here must have a determinant 0. So we can write for non-trivial, in other words, x is equal to 0, trivial solution A minus lambda I, determinant of that, should be equal to 0. Now, what is the determinant of this? Well, let's write put in our A here minus lambda I. What does it become? It becomes 1 minus lambda, and the 3 there is unaffected. The 2 is unaffected, and 2 minus lambda. Determinant of that is equal to 0. This here, this one here, which translates to that, is called the characteristic equation. Characteristic equation of our matrix A. Now, if this is equal to 0, let's expand the determinant. So we have 1 minus lambda multiplied by 2 minus lambda minus 2 times 3, which is 6, is equal to 0. This can also be written as lambda squared, I'm expanding it now, minus 3 lambda, this 2 and this 1, plus a 1 times 2, which is 2, minus this 6 here is equal to 0. Simplifying, we have lambda squared minus 3 lambda minus 4 is equal to 0. Now, we can solve this. We can choose the method we want. We can use the quadratic formula, or we can use factorization. I think it's easy to factorize, so let's do that. So this becomes equal to lambda here, brackets, lambda here, and what do we put here? Factors of 4 that subtract to, of minus 4 that subtract to 3, it's going to be 4 itself and 1. The 4 is minus, the 1 is plus, and this is equal to 0. So what is our solution? Our solution is lambda 1 is equal to minus 1, lambda 2 is equal to 4. So the eigenvalues of this matrix are minus 1 and plus 4. Now, let's see what happens to the the trace. What is the trace? The trace of a matrix is the sum of the elements in the leading diagonal. This one here and these two here. So the sum of that, I think I need something to rub this. Let me just quickly rub this, the top here. We don't need this, we need the eigenvalues. So I'll write this part here. So the next thing we want is the trace. Now the formula for the trace, we can just code it here. If a matrix has got eigenvalues lambda 1, lambda 2, lambda 3, etc., up to lambda n, then the trace of A, TR brackets A, is equal to lambda 1 plus lambda 2 plus lambda 3 all the way up to lambda n. Now, what is the trace of A? Trace of A is equal to 1 plus 2. 1 plus 2, which is equal to 3. Now, does that relate to our sum of the eigenvalues? Let's see. Eigenvalues are minus 1 and plus 4. So, lambda 1 plus lambda 2 is equal to minus 1 plus 4, which is equal to 3. So, this is equal. So, we can quote our formula as trace TRA is equal to sum of our general matrix A, lambda 1, lambda 2, all the way up to lambda n. I'm writing this for a general matrix A, which is an n by n matrix. Okay, so that's the relationship between the trace and the eigenvalues. Now let's see what is the determinant, what is the determinant of our matrix? Now det A, the determinant of A, the determinant of A is 2, 1 times 2 minus 2 times 3. It's 1 multiplied by 2 minus 2 multiplied by 3, which is equal to 2 minus 6, which is equal to minus 4. Now, what is let's try and multiply the eigenvalues. Now, lambda 1 multiplied by lambda 2 is equal to minus 1 here, minus 1 multiplied by 4, which is equal to minus 4. So this guy is equal to that guy. So it is true that the determinant of the matrix A, det A, is equal to, for an n by n matrix, it will be equal to lambda 1, lambda 2, lambda 3, all the way up to lambda n. So, to summarize, the trace of a matrix, which is the sum of the elements in the leading diagonal, is also equal to the sum of the eigenvalues. The determinant of the matrix, which we all know, for a matrix A, is always equal to the product of the eigenvalues. In other words, our eigenvalues here are minus 1 and 4, and that also happens to be the determinant of the matrix. These relationships can be used to simplify laborious calculations for the eigenvalues, which can be quite complicated when you are dealing with a 3 by 3 and above matrix. So you can rope in these two, one of them or both of them, to ease your calculations. If you enjoyed this video, please do subscribe, like, and share. In our next video, we are going to be dealing with the diagonalization of a matrix, quite related to this topic here. We're going to find eigenvalues, eigenvectors, and then finally diagonalize the matrix. Till we see you next time, bye-bye.